Swayam Prabha. Digital India. Educated India.
Now we are ready to solve the problem. First we have to understand how this cross section subject to inflation will deform due to Pi, the internal pressure Pi. Okay. Now first for that we have to understand how this circles will deform. Okay. What do you expect? You expect the circle to deform into another circle with an increased radius because you are inflating from inside. Okay. So basically what you expect is the circle to deform to another circle like that. Okay. You expect this inner circle to deform into a circle which is shown in red color here. Okay. Now similarly the outer circle will also expand and deform into another circle and will also deform to another circle as shown there. Okay. The displacement of the inner circle radially outward need not be same as the displacement of the outer circle in the same radial direction, that is this distance and this distance need not be the same because the cylinder thickness can change due to the application of this inner pressure, inside pressure. Okay. So that is one first observation. The second observation is, let us look at what happens to a line here, what happens to a radial line like that. The radial line like that will remain as a radial line except that it is going to now translate and move radially outward and maybe lengthen or shorten depending upon what happens to the thickness. It is going to become some straight line like that. Okay. It is not going to do something what I am drawing right now, it is not going to do something like that. Okay. It is not going to become a curved line, it is going to remain straight and it is going to move like that. Okay. So with this observations, now let us estimate or let us guess what the displacement field would be u in cylindrical coordinates. In cylindrical coordinates there is clearly a radial displacement of the circles. Okay. So there is a radial displacement of the circle, there is a radial component of the displacement field which will vary along the radius of the radial location of that circle, radial location of that point, because we said that the inner circle will not necessarily move the same distance as the outer circle moves. The inner circle can move more, outer circle can move less, there can be a thickness change. Okay. So it depends upon the radial location. Now if this radial displacement were to depend upon the circumferential coordinates theta, then what will happen is the circle will become an ellipse, which we said will not happen and hence is not a function of theta. In general this radial displacement will be a function of z because you have the ends fixed and hence what will happen is there will be a bulging of the cylinder, that is since the ends are fixed I will have the cylinder to bulge out like this and then this radial displacement should change with its axial location, but we will ignore that, saying the pipe is long enough and we are looking at the center portion of the pipe wherein it is more or less constant. Okay. So that is why we drop the z variation also. Okay. And hence we say that this radial displacement is dependent upon only the radial location of the point ER, plus we assume that there is no change in the straight line, is not deforming into a curved line. So there is no tangential or circumferential displacement of the point. So it is 0 times E theta plus I said that I am fixing the length of the cylinder. Okay. So I am assuming that there is no length change in the cylinder and hence there is no axial displacement also, 0 times Cz, there is no axial displacement. Since the cylinder is assumed to be fixed at both the ends. Okay. And this is no circumferential displacement. okay, because the cylinder is assumed to not rotate or twist due to the application of the inside pressure. Okay. Having found the guessed what a displacement field is,